There's something oddly comforting about mysteries that take their time unraveling, like a locked door in a forgotten hallway, or a puzzle box handed down for generations. You don't solve them right away. You sit with them. You trace their edges. You listen quietly for what they're trying to say. Black holes are like that. They've always felt more like questions than answers. Giant cosmic question marks, dressed in shadow. For most of history, we imagine them as perfect prisons, objects so heavy, so dense, that nothing, not even light, could escape. The universe's ultimate dead ends. And then something rather strange happened. They started glowing. Hello there and welcome to the Sleepish Science. Whether you're tuning in tonight or this afternoon, curled under a blanket or wandering through a forest of laundry on your bedroom floor, I'm glad you're here. If you feel like sharing, I'd love to know where you're listening from and what time it is for you right now. Personally, I'm broadcasting from a desk that thinks it's a library, with one too many mugs and exactly one confused houseplant. So before you drift into dreamland, go ahead and like and subscribe. Your future sleepy self will thank you, or at least give you a thumbs up in your dreams. Now, here's a curious truth. Black holes aren't really black, at least not anymore. The idea that they emit radiation, what we now call Hawking radiation, arrived like a cat walking across a chessboard. The theory didn't knock over all the pieces, but it rearranged the game. This unlikely revelation came from Stephen Hawking, the British physicist, whose wit was as sharp as his equations. It was early in the second half of the 20th century when he turned his attention to quantum mechanics and general relativity and realized maybe these two frenemies had more to say to each other than we thought. He began by asking what happens at the event horizon, that strange boundary around a black hole where escape becomes impossible. If quantum field theory, the framework that governs the jittery microscopic zoo of particles, still holds true near a black hole, then space itself must be buzzing with activity, even there, even at the edge, and in quantum field theory, even empty space isn't truly empty. It simmers with fluctuations. One moment, a patch of vacuum, the next a pair of particles popping into existence, one matter, one antimatter, before annihilating each other in a blink. It's like the universe can't stop nervously tapping its foot. Tolkien imagined this happening right at the event horizon. Suppose two such particles appear, just close enough to the edge. One falls in, the other escapes. From a distance, it would look like the black hole had just emitted something. Energy, radiation, a whisper from the dark. This idea was radical, not just because it suggested black holes aren't silent after all, but because it implied they lose mass as they radiate. Slowly, relentlessly. Evaporation not in a cloud of steam, but in a long, faint shimmer of quantum light. Now this isn't the kind of radiation you or I would notice. You wouldn't get a tan from it. If you stood beside a solar mass black hole and waited for it to warm your toes, well, you'd be there a very, very long time. For most black holes, Hawking radiation is laughably weak, like trying to hear a pin drop during a thunderstorm. But over cosmological spans across timescales so vast they make ancient ruins seem like toddlers, it adds up. This process, though slow, rewrites the destiny of black holes. No longer eternal, no longer immune to the tick-tock of the universe. A black hole, given enough time, will evaporate into nothing at all. And what's more, this radiant leak cracks open an ancient philosophical chest. Can information be truly lost? If a black hole devours your sock drawer, or a sun, or an entire novel, where does the pattern of that stuff go? The atoms, sure, are gone. But what about the shape of them, their relationships, their history? We'll tiptoe further into that later. But for now, what matters is this Hawking's idea didn't just give black holes a way out. It gave physics a new riddle to chew. You might be wondering, has anyone actually seen this radiation? The answer is a sheepish no. Not yet. Hawking radiation is so faint that for any known black hole, it's drowned out by cosmic noise. It's like trying to find the heat from a birthday candle while standing on the surface of the sun. Still, its theoretical foundation is strong. So strong, in fact, that in 2019, physicists Jeff Steinhauer and collaborators at the Technion Institute in Israel built a model of a black hole using sound waves in a cold atom cloud, and they claim to observe an analogue of Hawking radiation. A sonic black hole, if you will. But more on that curious experiment in a later tale. The key idea to hold on to is this: even the darkest things in the universe aren't entirely silent. If quantum mechanics is to be believed, then every black hole is a slow-burning ember, humming softly through the fabric of space-time. Of course, this also means that black holes, once considered permanent features of the cosmos, are now understood to be mortal, extremely long-lived, but not immortal, like glaciers or bureaucracies. And if that doesn't make you look at the sky a little differently, I don't know what will. Even the quietest parts of the universe are never truly silent. If you could somehow float, utterly alone, in what looks like empty space, no stars, no planets, not even a whisper of stardust, you might imagine yourself in perfect stillness. But stillness, in quantum mechanics, is a kind of illusion. There's always motion underneath, always a hum, a flicker, a murmur at the edge of what can be known. This is where the story turns intimate, to the scales far smaller than atoms, where quantum field theory begins to describe the restless heart of space itself. Quantum field theory is in essence our best attempt at describing everything that twitches. It tells us that what we call particles are just excitations, tiny ripples, in fundamental fields that stretch across the entire universe. There's a field for every kind of particle you've heard of: electrons, neutrinos, quarks, and all their jittery companions. Even the photon, the bundle of light, emerges as a ripple in its own electromagnetic field. Now picture space near the event horizon of a black hole, not close enough to be pulled in just yet, but near enough to feel the curvature of space-time gently tugging at your atoms. In this zone, this twilight of gravity, quantum fields are still active. They jitter, just as they would anywhere else. And from this jitter something peculiar emerges: virtual particle pairs. These pairs are a consequence of what's called the uncertainty principle. It's not just that we can't know both the position and momentum of a particle, it's that space itself must allow a little wiggle room. Enough wiggle, it turns out, for pairs of particles to spontaneously blink into existence for a brief, borrowed moment. Normally, these pairs annihilate quickly. One particle is matter, the other antimatter, their energies cancel, and the universe stays tidy. But when these pairs form at the event horizon, things get untidy in a fascinating way. Let's imagine a pair is born just straddling the edge of the black hole. One particle zips off into open space, the other tumbles into the black hole. Now the particle that escaped no longer has a partner to annihilate with. It becomes real in the language of quantum mechanics. Not just a jitter, but a proper little something, an actual bit of energy, racing away. To make up for this energy, the universe keeps very strict books. After all, the black hole loses a tiny fraction of its mass. It's as if it had paid a toll for letting go of that escaping particle. This is the engine of Hawking radiation, a particle escape artist act funded by the black hole's own weight. It's worth noting, the escaping particle doesn't technically come from inside the black hole. That's what makes this process so strange. Nothing actually escapes the interior. Rather, it's the field fluctuations just outside the event horizon that do the work. The horizon acts like a one-way membrane, breaking apart the temporary union of these quantum couples, a celestial marriage counselor, if you will, with a fondness for separation. There's more subtlety here than can fit in a single metaphor. For example, what counts as the vacuum near a black hole depends on your perspective. This is called the observer-dependent nature of particle states. A scientist far from the black hole sees an outgoing particle and says, "Look, Hawking radiation." But another scientist riding along with the particle that falls in might insist there was no radiation at all, just a smooth crossing of the horizon. Like arguing whether a firework is loud, depending on whether you're under it or underwater. This observer dependence arises because general relativity and quantum field theory each define time differently. Near a black hole, space and time warp dramatically, so even the idea of what exists becomes slippery. A particle in one frame may be vacuum in another. A very literal case of perspective making reality. To illustrate this, we can draw from research by William Unruh, who in the latter half of the 20th century showed that even acceleration through space can cause you to perceive a warm glow of particles in an otherwise cold vacuum. This so-called Unruh effect suggests that movement alone can conjure heat from emptiness, something eerily parallel to the glow seen near black holes. So what we have then is a quantum field that never sleeps, a surface of no return that severs partnerships, and a cosmic ledger that demands payment in mass. All wrapped up in a dance of perception and reality. It's enough to make your head spin. if your head weren't already caught in gravitational time dilation. The consequence of this elegant but mind-bending framework is that the universe itself behaves like a magician. Nothing up its sleeve, yet particles appear. A performance carried out at the border between two of physics' most cherished theories, general relativity, which governs gravity and space-time, and quantum mechanics, which governs everything small and squiggly. These two frameworks aren't exactly friends. They coexist like roommates who label their milk. But here at the event horizon, they are forced into an awkward conversation, each whispering secrets to the other, revealing truths they'd otherwise keep tucked in their own equations. And still, despite all this theorizing, there remains one inconvenient fact. No one has yet seen a single particle of Hawking radiation directly. It's all theory, all inference, all delicate mathematics resting atop the thinnest reeds of cosmic logic. But that's not unusual in physics. The neutrino was once a ghostly suggestion. Gravitational waves were a rumor for a century. Science, too, is patient. It listens, it waits, and black holes, for all their silence, may yet speak. If you were to take the universe at its word, the classical word, the Newtonian word, the gravitation governs all word, you'd believe that black holes are utterly dark. They consume everything, reflect nothing, and emit not a single whisper of light. They are, in that old model, the purest form of silence in space. But as we've begun to see, quantum physics has a way of peeking behind even the most firmly closed curtains. So what happens when the lightless turns luminous? It starts not with a bang, but with a glow so faint that calling it glow almost feels like flattery. Imagine, if you will, a bonfire whose embers are cooled not by wind, but by the stretching of space-time itself. The Hawking radiation emitted by a black hole is just such an ember, a slow exhalation of energy that defies classical expectations. Let's take a moment to understand how unlikely this is. In general relativity, the theory gifted to us by Albert Einstein early in the 20th century, a black hole is defined by the presence of an event horizon, a boundary from which nothing, not even light, can escape. Once something crosses it, that something is gone to us, severed from our observable universe. All paths, from that point forward, lead inward. But quantum field theory disrupts this narrative. It adds fine print to the cosmic contract. The key lies in the behavior of the vacuum near the event horizon. As we explored earlier, quantum fields are never truly still. They're always jostling, always generating short-lived pairs of particles and antiparticles. This jittering allows energy to leak in a way that classical gravity does not predict. So even as general relativity declares black holes as perfect absorbers, quantum mechanics gently protests, but they can radiate. This disagreement leads us to a strange conclusion. Black holes are not truly black, they shine, in the faintest way imaginable. Now, the temperature of this radiation depends inversely on the mass of the black hole. The more massive it is, the colder it becomes. A black hole formed from a collapsed star, for example, would emit radiation at a temperature far below that of the cosmic microwave background, the faint afterglow left from the early universe. This means its radiation is drowned out by the ambient warmth of space itself. It's like trying to spot a birthday candle in the middle of a desert at high noon. The light is technically there, but good luck seeing it. And yet, the theory holds. It is mathematically rigorous, emerging from the union of general relativity's curved space-time and the statistical tools of thermodynamics. Stephen Hawking himself derived the equations using a technique called the path integral formulation, developed by Richard Feynman. This method imagines every possible trajectory a particle might take, summing them all into a kind of quantum average. From this ocean of possibilities, the glow of Hawking radiation arises, not as a miracle, but as a necessary conclusion. The radiation itself is nearly perfect thermal radiation, meaning it follows the rules of a black body spectrum. That might sound contradictory, but in physics, a black body is an idealized object that absorbs all incoming radiation and re-emits it based on its temperature. The irony is not lost. The blackest object in the universe is in fact a textbook example of a black body emitter. This connection brings us to a beautiful unity in physics. In the early 20th century, Max Planck's work on black body radiation gave birth to quantum theory. A century later, black holes themselves became the ultimate black bodies, completing a poetic loop in the structure of science. But poetry aside, This glow has consequences. It implies that black holes have entropy, a measure of disorder or information content. This was first hinted at by Jacob Bekenstein, a physicist who argued that the surface area of a black hole's event horizon might be related to its entropy. Hawking's discovery confirmed this, showing that black holes aren't just thermodynamic oddities, they obey a kind of thermodynamic law book. They have temperature, entropy, and now radiation. They are not dead. They are deeply alive in the language of physics. That radiation, though, is peculiar. It carries no memory. It's featureless. If you tossed a grand piano into a black hole, the resulting Hawking radiation wouldn't hum middle C or carry a trace of mahogany. It would look exactly the same, as if you'd thrown in a bowl of soup or your most embarrassing high school diary. The outgoing particles remember nothing of what fell in. This leads to one of the thorniest puzzles in modern physics, but we'll save that philosophical tangle for a little later. For now, let's sit with this moment. Black holes radiate. They shine, even if only faintly. They are thermodynamic objects, not just gravitational sinkholes, and through this radiation, they gradually lose mass. The universe, in its quiet persistence, tells us that nothing is permanent, not even something that once seemed eternal. This realization has inspired a cascade of new ideas. Some physicists have attempted to observe this effect in laboratory conditions using analog systems like Bose-Einstein condensates and optical fibers. While these models don't replicate gravity itself, they do mimic the behavior of fields near an event horizon, and in some of them, researchers have detected radiation that resembles Hawking's prediction, albeit in very different forms of matter. In 2010, a team led by Ulf Lionheart at the University of St Andrews created optical analogues that showed potential Hawking-like emission. Their setup used refractive index gradients in optical fibers to simulate a horizon for photons, and while the results remain debated, they illustrate just how far physicists are willing to go to eavesdrop on a black hole's whisper. Meanwhile, theoretical physicists continue refining their models. String theory, loop quantum gravity, and other contenders for a unified theory all wrestle with the implications of this emission. Each new insight reshapes our understanding of what it means to cross that invisible border, the horizon that both hides and reveals. Of course, in the tradition of cosmic irony, the very process that makes black holes visible also ensures their eventual demise. As they emit radiation, they shrink, slowly, silently, they evaporate. A candle burning, not from its wick, but from its shadow. And the question that lingers, as always, is what do they leave behind? Some relationships are brief but meaningful. A glance across a room, a passing kindness from a stranger, or in this case, a pair of virtual particles, sharing the tiniest sliver of time before the universe pulls them apart. These fleeting duos are the true protagonists in the story of Hawking radiation. Their breakup, orchestrated at the edge of a black hole, reveals not just how black holes lose mass, but how quantum physics reshapes our most basic assumptions about emptiness, energy, and existence. Let's revisit this idea with a slightly clearer lens. The vacuum, according to quantum field theory, is a restless sea. At every point in space, energy fluctuates. The vacuum is not still. It bubbles briefly with particle-antiparticle pairs that appear and vanish in what seems like spontaneous rebellion against the notion of nothing. These are not real particles in the conventional sense. They are virtual, borrowing energy from the vacuum for a moment so short that Heisenberg's uncertainty principle allows it. It's like cosmic shoplifting, but with a receipt that vanishes before the register beeps. Under ordinary conditions, these pairs cancel each other out. One is matter, the other antimatter. And when they meet again, they self-destruct, leaving no trace. But near the event horizon of a black hole, this perfect symmetry is disturbed. The gravitational pull is so extreme that the horizon itself acts like a one-way membrane. Anything passing inward cannot return. So if one of these particles finds itself just inside the horizon, while its partner remains just outside, their reunion is permanently cancelled. The consequences of this missed rendezvous are profound. The particle that escapes becomes real, and real particles carry energy. The one that falls in paradoxically carries negative energy relative to the outside universe. That idea might sound like science fiction, but it's a genuine outcome of general relativity in curved space-time. By absorbing this negative energy intruder, the black hole loses a sliver of mass. It's a kind of cosmic accounting to let one particle go. the black hole pays a toll. It shrinks, ever so slightly. The brilliant twist here is that the escaped particle, born from what seemed like vacuum, appears to an external observer as radiation. This is Hawking radiation, not because it emerges from the black hole's core, but because it's a side effect of the horizon's interaction with the vacuum's jitter. The energy doesn't come from the inside, it comes from the curvature of space-time and the strange bookkeeping of quantum fields. Stephen Hawking's calculations, published in the mid-70s, were initially met with disbelief, not just because they suggested that black holes evaporate, but because they emerge from well-established physics. His math relied on semi-classical gravity, a framework where quantum fields operate on a fixed classical background. It wasn't a new theory, it was a collision between old ones. Jacob Bekenstein had already paved part of the path. He suggested that black holes must have entropy, that is, a measure of their internal disorder. His argument, controversial at the time, was that tossing something into a black hole shouldn't reduce the total entropy of the universe. Therefore, the black hole must gain entropy in response. And if it has entropy, it must have a temperature. Hawking's discovery proved Bekenstein right, and added the final twist: temperature implies radiation. The thermodynamic puzzle was complete. From a physics standpoint, what makes this process so elegant is its inevitability. It doesn't depend on the material that fell into the black hole or the type of black hole it is. All that matters is the presence of the horizon. The key ingredient isn't mass or spin or charge, it's geometry. The event horizon is the real actor in this drama, and its geometry, curved by the immense gravity of the black hole, reshapes the rules of energy and time. A helpful analogy comes from the world of optics. Imagine a prism splitting white light into a rainbow. The prism doesn't create color, it just reveals what was already there, hidden in the beam. Similarly, the black hole doesn't create particles in the traditional sense. It reshapes the vacuum in such a way that the underlying energy reveals itself as radiation. There's even a parallel to be found in the Casimir effect, a phenomenon observed when two metal plates are placed very close together in a vacuum. Because only certain quantum wavelengths can fit between the plates, a pressure difference emerges, pushing them together. This is real, measurable energy arising from quantum vacuum fluctuations. The vacuum isn't empty, it never was. In the black hole case, the role of the plates is played by the horizon. It acts as a boundary, altering which quantum fluctuations are allowed. The result is not a push, but a slow leak of radiation, over immense timescales. This adds up. The black hole emits energy, it cools, it shrinks. This emission process, however, introduces a thorny issue: information. The Hawking radiation that escapes carries no signature of what fell in. If you drop a book into a black hole, a romance novel, say, or a physics textbook, the radiation that eventually emerges contains no trace of its contents, just a bland mix of particles that suggests that information about the book is lost forever. But this contradicts a central tenet of quantum mechanics: unitarity. In simple terms, unitarity says that information cannot be destroyed. It may be scrambled, it may be encoded in ways we don't understand, but it persists. And this leads to the infamous black hole information paradox, a puzzle that has fueled decades of debate and countless conference coffee breaks. Some physicists believe the information is preserved on the horizon itself, in a kind of holographic imprint. Others argue that the radiation somehow carries it away, in a code we haven't yet cracked. A few even suggest that black holes don't evaporate fully, but leave behind stable remnants, tiny dense nuggets of compressed data. But that's for another evening. For now, what matters is this: when a particle pair forms at the edge of a black hole, and one falls in while the other escapes, something real happens, something irreversible. The black hole pays for that escape with its mass. The horizon shifts, the universe sighs, and across vast distances, in telescopes not yet built and laboratories not yet imagined, we may one day catch the faint echo of that quantum transaction, the receipt finally visible. If you've ever stared into the night sky and wondered whether the universe is listening, you're not alone. Astronomers have been listening for decades, not for whispers of human origin, but for cosmic murmurs that hint at secrets buried in blackness. And now, and then amid the electromagnetic rustle of galaxies and pulsars, something unusual arrives. Not quite a shout, not exactly a whisper, more like the high-pitched giggle of a cosmic jet engine. These clues come to us not from black holes sitting quietly in the dark, but from the rowdy cousins known as microquasars. A microquasar is a stellar mass black hole or neutron star that feeds hungrily on a nearby star, producing powerful jets that shoot matter into space at nearly the speed of light. They're called micro not because they're small, they're still enormous, but because they are scaled-down versions of quasars, the active galactic nuclei powered by supermassive black holes. Quasars live at the hearts of galaxies. Microquasars live in binary star systems right in our own galactic backyard. One such object is GRS, discovered in the mid-90s by NASA's Rossi X-ray Timing Explorer. Located thousands of light-years away, this black hole and its stellar companion form a dramatic pair. Matter from the companion spills toward the black hole, spiraling in a bright, hot disk of infalling plasma. The system emits in radio, X-ray, and infrared, and features jets that pulse with uncanny regularity, earning it the nickname the heartbeat black hole. These jets are not Hawking radiation, let's be clear about that. But they demonstrate something important. Black holes can be luminous, active, and astonishingly complex. In systems like GRS, the radiation doesn't come from the black hole itself, but from the accretion disk and the shock waves created as material falls inward. The disk heats to millions of degrees, emitting X-rays, while magnetic fields channel some of the matter into bipolar jets that stream outward, like twin cosmic fire hoses. While these jets aren't a direct sign of black hole evaporation, they offer indirect support to the idea that black holes aren't entirely dark. The region near the event horizon is a wild, turbulent place. Matter glows, space-time wobbles. Magnetic fields twist into knots and fling particles out at speeds that make Formula One look like a tricycle race. In 2010, a study led by John Tomsic at the University of California, Berkeley, used data from the I-integral satellite to observe Cygnus X1, one of the first suspected black holes ever identified. The observations revealed evidence of X-ray polarization, providing clues about the geometry of the disk and jets near the event horizon. This helped confirm that the radiation we see is not uniform but structured, a product of extreme conditions and relativistic motion. These systems also allow us to test general relativity in the strong field regime. As material orbits close to the black hole, it experiences time dilation, gravitational redshift, and frame dragging, the twisting of space-time predicted by Einstein. Observations of iron spectral lines in the X-ray emissions show broadening consistent with these relativistic effects, confirming that these are indeed real black holes, not just neutron stars in disguise. But perhaps even more tantalizing than microquasars are the hypothetical relics from the very early universe, primordial black holes. Unlike those formed by collapsing stars, primordial black holes may have been born shortly after the Big Bang, formed by density fluctuations in the rapidly expanding young cosmos. They could range in size from microscopic to several times the mass of Earth. Physicists like Bernard Carr and Stephen Hawking proposed these objects in the 1970s, imagining them as possible components of dark matter or as early seeds for galaxy formation. If such black holes exist, and if any of them are sufficiently small, they may be evaporating now, right this very moment, via Hawking radiation. This idea has inspired numerous searches. The Fermi Gamma Ray Space Telescope, for instance, has been on the lookout for brief gamma-ray bursts that could indicate the final moments of a black hole's life. These bursts would be incredibly short-lived and high-energy, perhaps lasting just a fraction of a second, but they'd be definitive proof that Hawking radiation is more than a mathematical whisper. So far, no unambiguous signal has been found, but the search continues, and even without direct detection, the observational landscape is rich. The Laser Interferometer Gravitational Wave Observatory, known for catching the tremors of black holes colliding, has opened a new chapter in black hole astronomy. With each collision, we learn more about their masses, spins, and prevalence. Some of the black holes detected by LIGO are in mass ranges that challenge our understanding of stellar evolution, leading some to speculate they could be primordial. Meanwhile, black hole candidates and distant galaxies continue to surprise us. One such case is HLX-1, located in the galaxy ESO 243. It emits X-ray bursts that suggest the presence of an intermediate mass black hole, neither stellar mass nor supermassive. These in-between objects are hard to classify, but they may offer clues about how black holes grow, merge, and evaporate. All of this observational data, microquasars, gamma-ray searches, gravitational wave detections, builds a case for a new understanding. Black holes, though defined by what they hide, are gradually revealing themselves. They're not just endpoints, they're participants. They influence galaxies, shape the growth of stars, and radiate more than we once believed possible. If we follow the clues, flickers in X-rays, bursts of jets, gravitational echoes, we begin to see a picture forming. A black hole isn't simply a void, it's an active node in the cosmic network, interacting with the universe in ways both violent and subtle. And as we listen carefully, these once silent giants begin to speak, not in roars but in radiant clues. If you've ever opened a cluttered drawer and wondered how so much chaos fits in such a small space, you've already shared a kindred thought with physicists puzzling over black hole entropy. For all their mystery and menace, black holes are surprisingly neat about their messiness, but not in the way you might expect. In fact, when it comes to storing disorder, or information, or surprise, black holes don't use their volume, they use their surface. This notion didn't come from some dreamy speculation, but from a stubborn insistence on consistency. In the early 1970s, physicist Jacob Bekenstein was thinking about entropy and how it plays with gravity. Entropy, in classical thermodynamics, is often described as a measure of disorder. The more possible arrangements a system can have, the higher its entropy. A tidy room has low entropy. A tornado in a toy store, considerably more. Bekenstein noticed something troubling. If you throw a cup of tea into a black hole, an act which one hopes is metaphorical, the entropy of the universe should decrease. The cup and its contents had many configurations. Once inside the black hole, all that information disappears. But thermodynamics insists entropy should never go down. So where did all that disorder go? His proposal was bold. Maybe black holes themselves have entropy, and that entropy is proportional not to their volume but to the area of their event horizon. It was a strange idea. Normally we expect the more stuff you have, the more space it takes up, and the more room there is for disorder. But black holes flipped that logic. The more mass a black hole has, the bigger its event horizon becomes, and so the more area it has to store entropy. This radical suggestion gained support when Stephen Hawking's calculations confirmed that black holes radiate. If they emit radiation, they must have temperature, and if they have temperature, they must obey the laws of thermodynamics. That meant they also had entropy, and Bekenstein's area law became law, not just metaphor. Mathematically, the entropy of a black hole is staggeringly large. For a black hole with the mass of our Sun, its entropy is about 10 to the 77th power in Boltzmann units. That's a 1 followed by 77 zeros. Compare that to a roomful of gas molecules, or even a galaxy's worth of stars. Black holes beat them handily. They're entropy champions. This raises profound questions. If entropy is a measure of information, and black holes have such high entropy, what exactly is being stored? Every particle, every photon, every awkwardly thrown pizza crust that falls in, what happens to the pattern it once formed? Is the structure lost, or just scrambled? This is not just a philosophical riddle. It strikes at the heart of physics. According to quantum mechanics, information must be preserved. Processes might be reversible, even if they look messy. But when information falls into a black hole and the black hole evaporates, where does that information go? That's the black hole information paradox, and entropy is the hinge on which it swings. Some researchers have suggested that the information is somehow encoded on the event horizon itself. This idea gained traction with the development of the holographic principle, which we'll explore in depth later. But the root of the idea is deeply tied to entropy. If a black hole's entropy is stored on its surface, maybe all the information about what's inside is too. Leonard Susskind, a leading voice in theoretical physics, famously clashed with Stephen Hawking over this paradox. Hawking believed information was lost. Susskind argued it must be preserved. The disagreement played out over conferences, debates, and decades. In the end, most of the physics community leaned toward preservation, though the exact mechanism remains mysterious. Meanwhile, the second law of thermodynamics was updated to include black holes. Now we talk about the generalized second law: the total entropy of the universe, including black holes, must never decrease. This helps preserve the grand bookkeeping of physics, where no information is truly thrown away, only moved or masked. Interestingly, this idea isn't just abstract. It influences how we think about the early universe, where high energy densities could have created tiny primordial black holes. If these evaporated quickly, they would have contributed both energy and entropy to the young cosmos. The relics of such events might still be embedded in the patterns of the cosmic microwave background, the oldest light we can see. There's also a compelling link to black hole mergers. When two black holes collide, as detected by LIGO, their horizons combine. The area of the new larger horizon is greater than the sum of the two smaller ones. This follows the area theorem, originally proposed by Stephen Hawking, which states that the total area of black hole horizons can never decrease, much like entropy itself. These ideas converge on a remarkable insight. Entropy and information are not just metaphors in black hole physics. They are literal quantities, calculable and consequential. They tie together the thermodynamic, gravitational, and quantum natures of the universe into a single, elegant knot. And so we arrive at a strange truth. The black hole, that most opaque of cosmic objects, is also one of the most informative, not in the sense that it tells you things easily, it most certainly does not, but because it holds more information than almost anything else in the universe. We just don't know how to read it. Like a locked drawer with a stubborn keyhole, the black hole promises secrets beyond comprehension. Its entropy tells us they're in there, somewhere. Imagine writing a heartfelt letter, sealing it in an envelope, and watching it tumble into a fireplace, only to be told years later that the ashes still somehow contain the message. That's not unlike the tension that lives at the heart of one of physics' most enduring puzzles, the black hole information paradox. It's the dilemma that arises when two of our most trusted theories, quantum mechanics and general relativity, disagree over what happens to information swallowed by a black hole. According to quantum mechanics, the laws of physics are reversible. This doesn't mean you can untoast your bread, but rather that, in theory, the equations describing quantum particles can be run backward. Every quantum process preserves information. That includes the shape of a molecule, the alignment of a particle's spin, even the awkward trajectory of a banana flung across space. Nothing is ever truly forgotten, just entangled, obscured, or dispersed. But general relativity plays by different rules. When something crosses a black hole's event horizon, it's gone for good, at least from the perspective of any external observer. The mass remains, the charge, maybe even the angular momentum, but all the detailed information about what fell in seems to vanish from the universe. As the black hole emits Hawking radiation and slowly evaporates, that information doesn't seem to come out. It's as though the letter has turned to ash, and the ashes have no memory of ink. This is not just a metaphysical annoyance. It's a problem of principle. If information can be destroyed, quantum mechanics as we know it would collapse. The foundations of quantum theory, its unitarity, its predictability, its dazzling mathematical structure, would be shaken. And physicists do not like their foundations shaken. This paradox took shape in the late 1970s, after Hawking's radiation paper landed in the world of physics like a polite thunderclap. At first, many physicists thought the issue might be a technical misunderstanding, but as the calculations were refined, the paradox only deepened. The radiation, it turned out, was thermal, random. It carried no record of what had fallen in. If a black hole completely evaporates, then the details of everything it consumed would vanish too. That's forbidden in quantum mechanics, but allowed in classical gravity. Enter the great debate. Stephen Hawking defended the position that information was lost, insisting that quantum gravity must accommodate this loss in a consistent way. Leonard Susskind, Gerard Hooft, and others pushed back, arguing that something was missing from Hawking's picture. Over time, the consensus began to shift. More and more theorists concluded that somehow the information must survive. The question then became, how? One proposal, known as black hole complementarity, suggests that information is both reflected at the horizon and absorbed into the black hole, but never observed in both places at once. This interpretation attempts to preserve both quantum unitarity and the predictions of general relativity by insisting that no single observer ever sees a contradiction to a distant observer. The information never quite crosses the horizon. To an infalling observer, it crosses easily. Both are right, but they cannot compare notes. If that sounds unsatisfying, you're in good company. The idea feels a bit like a cosmic version of Schrödinger's cat, both burned and not burned, depending on who's watching. But it does offer a way to preserve unitarity without discarding the logic of general relativity. Then, in the early 21st century, the holographic principle emerged as a front-runner in resolving the paradox. Spearheaded by Juan Maldaceno's work in what's known as the CFT correspondence, this principle proposes that all the information contained in a volume of space can be described by information encoded on its boundary, just as a two-dimensional hologram can project a three-dimensional image. Applied to black holes, the idea is radical. Perhaps everything that falls into a black hole is somehow encoded on its event horizon. The surface becomes a kind of data sheet, recording the quantum state of the infalling matter. From a certain mathematical standpoint, the black hole is a hologram storing its secrets not in depth but in surface. If this is true, then Hawking radiation might not be featureless after all. Instead, it might carry subtle correlations, patterns too faint to notice at first glance, but containing all the information needed to reconstruct the original contents. The information isn't lost, it's just very scrambled. In recent years, further developments have added nuance. The firewall paradox, introduced in the early 2010 by Olmheri, Marolf, Polchinski and Solly, questioned whether the interior of a black hole could even exist in the way general relativity suggests. If information is encoded at the horizon, then perhaps something dramatic happens there, a wall of high-energy particles incinerating anything that tries to pass through. This firewall proposal challenges the very notion of a smooth horizon and has ignited fierce debate. Meanwhile, efforts to calculate black hole entropy using quantum entanglement have led to the concept of islands in space-time, regions where quantum information can be said to localize. These calculations have yielded page curves that match what's expected if information is conserved. Entropy rises, then falls as the black hole evaporates, suggesting that radiation does eventually carry the information away. Still, these ideas rely on new frameworks of quantum gravity, many of them speculative. Loop quantum gravity, string theory, and other approaches each offer tools for thinking about the problem, but none has yet been confirmed. The black hole information paradox remains unresolved, not because we lack theories, but because we lack a definitive test. And so, physicists continue to probe, not with sticks and ropes, but with equations, analogies, and carefully measured X-rays. They turn to analog black holes in labs, sift through gravitational wave data, and dream up thought experiments that strain the imagination. This paradox has become more than a puzzle. It's a proving ground for new physics. Like a cosmic Rorschach test, it reveals what we value in our theories: predictability, elegance, completeness. At its core lies a quiet plea: let the universe make sense. And maybe, buried in the very fabric of space-time, that letter we thought was burned still waits, written not in ink but in the gentle curve of the horizon. There's a curious poetry to the way science imitates nature, lacking the luxury of poking an actual black hole with a long stick. However tempting that may be, physicists do what humans have always done in the face of the unpoken. They build analogues. In place of real black holes, they construct tabletop echoes, hoping these miniature mimics can reveal something about the real giants haunting space. Among the strangest of these doppelgangers are sonic black holes, fluid systems designed to trap sound the way real black holes trap light. Let's begin with a simple idea. A black hole is defined by its event horizon, the point beyond which nothing, not even light, can escape. Replace light with sound, and you have the basic concept behind a sonic black hole, also called an acoustic black hole or dumb hole. In these systems, the flow of a medium, often a Bose-Einstein condensate or superfluid helium, is manipulated so that it exceeds the local speed of sound in some region. Any sound wave trying to move upstream is dragged backward, unable to escape. It's trapped, not by gravity, but by the fluid's relentless motion. The analogy may sound whimsical, but the mathematics lines up. In 1981, physicist William Unruh proposed that sound waves in a moving fluid obey equations nearly identical to those governing scalar fields in curved space-time. That meant you could, in principle, simulate aspects of general relativity using water, light, or ultracold atoms. Black hole behavior, particularly Hawking radiation, might be studied in the lab, not by recreating gravity, but by reproducing its effects. Fast forward a few decades, and Unruh's brainchild became a playground for experimentalists. In the early 21st century, physicists began crafting analog horizons in optical fibers, water channels, and ultracold atomic gases. Among the most notable was a 2016 experiment led by Jeff Steinhauer at the Technion, Israel Institute of Technology. Using a Bose-Einstein condensate, a cloud of atoms cooled to near absolute zero. His team created a region where the flow of the condensate exceeded the local speed of sound. This acted as a sonic event horizon, and just as Hawking predicted, the team reported the emission of paired phonons, quantum units of sound, straddling the horizon. In essence, they saw the sonic equivalent of Hawking radiation. Now, it's important to temper the excitement. These experiments do not confirm Hawking radiation from astrophysical black holes. The physics is analogous, not identical. The fields involved, the particles emitted, the energies measured, all belong to a different regime. But they do lend support to the core concept that horizons, regardless of their origin, can generate radiation due to quantum effects. This is the brilliance of analog gravity. It allows us to test our theories in regimes we cannot otherwise access. By watching how phonons emerge in a cold lab, we gain insight into how photons might escape the gravitational grip of a black hole. Other experimental approaches have joined the effort. In 2010, Belgiano and colleagues used ultra-short laser pulses in optical fibers to create refractive index perturbations that mimic event horizons. These optical horizons showed signs of spontaneous emission, sparking debate over whether they truly represented analog Hawking radiation. Critics pointed out inconsistencies, but the experiment sparked new lines of inquiry. Still, other teams have used water tanks. In one memorable demonstration, researchers created a flowing channel with a submerged obstacle that accelerated the surface flow. Ripples approaching this region slowed, then were swept back, unable to climb the oncoming current. While these macroscopic systems lack the quantum nuance of atomic analogues, they beautifully illustrate the core geometry of horizons, a boundary defined not by walls but by the behavior of waves. What ties all these systems together is a shared language. Whether in superfluids or light pulses, we're learning how horizons manipulate fields. We see pair creation, we see asymmetric emission, we see the signs of entanglement between regions separated by a horizon. And that's not just academic, it offers a possible path forward in resolving the information paradox. If we can understand how analog horizons process information, how their emitted radiation is correlated, we might gain clues about real black holes. The experiments act like thought experiments made tangible, little universes in beakers and fiber loops. Moreover, these analogues remind us that gravity, despite its grandeur, is not untouchable. Its behaviors, at least in some regimes, are mirrored in systems we can build. That mirroring is not mere mimicry, it's a tool. It suggests that space-time itself might be emergent, like a fluid's flow. This idea, explored by thinkers like Ted Jacobson and Eric Valindi, posits that gravity may arise from thermodynamic or quantum informational principles rather than being a fundamental force. If that's true, then studying the physics of analog horizons might teach us not only about black holes, but about gravity itself. It reframes our most venerable force as something born from entropy, from information processing, from statistical mechanics. A tide, not a tug. Of course, much remains unproven. The field of analog gravity is young, and many experiments are controversial. Reproducing the exact conditions of Hawking's calculations remains an ambitious goal, but the very attempt illustrates a shift in our approach from distant awe to engaged curiosity. From watching black holes with telescopes to emulating their whispers on lab benches. And isn't that just the story of science? When the universe places something impossibly far away, we try to recreate its shadow nearby. We listen to the echo. We light the match and watch how it flickers. One day, perhaps, the final proof of Hawking radiation will come not from a telescope, but from a petri dish. Until then, we build our simulacra, measure their emissions, and wonder if a black hole sings in a laboratory, will the cosmos hear it too? The universe, despite its immensity, is a patient sculptor. It chisels away at even its most titanic structures over unimaginable spans of time, like a glacier sanding down mountains. And perhaps the slowest of its sculptures, the most delicate of erosions, is the gradual evaporation of black holes. It's not a process that unfolds in lifetimes or even civilizations, but over spans so vast that if you tried to count them, you'd need more fingers than there are atoms in your body. Still, even this quietest of farewells has a final act, and it's not without a certain flourish. To understand the full arc of a black hole's life, we must return to Hawking radiation. As we've established, black holes emit radiation through the separation of virtual particle pairs at the event horizon. This radiation carries energy away, and by the laws of conservation, the black hole must lose mass in the process. The more it radiates, the smaller it gets. The smaller it gets, the hotter it becomes. And the hotter it becomes, the faster it evaporates. It's a feedback loop, a slow whisper that accelerates into a scream. The mathematics is elegant in its inevitability. Early in the black hole's life, the emission is negligible. For a stellar mass black hole, the temperature is lower than the cosmic microwave background, the thermal radiation left over from the Big Bang. In this early stage, the black hole gains mass more easily than it loses it. It's a cosmic hoarder, swallowing more than it leaks. But as the universe ages and cools, the balance tips. Once the ambient temperature dips below the black hole's temperature, Hawking radiation begins to dominate. The black hole loses more than it gains, and from that moment on, it's on a one-way path to non-existence. This final phase, though still theoretical, is the subject of much speculation. As the black hole shrinks, its temperature increases, eventually reaching levels where it radiates significant amounts of energy in very short spans of time. The last seconds of a black hole's life are expected to be an intense burst of high-energy radiation, possibly including gamma rays and exotic particles. A kind of final pop, not unlike the quiet snap of a soap bubble breaking against the void. Such an event, were it to occur within observational reach, would be dramatic. And it's precisely this idea that drives some astronomers to search the skies for short-lived unexplained flashes of high-energy light. These searches focus on hypothetical primordial black holes, tiny black holes that may have formed in the very early universe, before stars, before galaxies, before even the atoms we know today had coalesced. If any of these primordial black holes were small enough, they might be reaching the end of their lives right now. Gamma-ray observatories like NASA's Fermi Space Telescope and ESA's Eye Integral have looked for such final flashes. Thus far, no definitive bursts have been attributed to black hole evaporation, but the search continues, guided by theoretical predictions and patient algorithms. The late stages of black hole evaporation also raise questions about what happens at the smallest scales. As the mass approaches the so-called Planck mass, the tiny unit of mass where quantum gravity effects become significant, our current theories start to blur. General relativity, which describes gravity so beautifully on large scales, begins to falter. Quantum field theory, which handles the small and squiggly, lacks the gravitational teeth to go all the way. We enter a realm where new physics is needed. Some theories suggest that evaporation stops just shy of full disappearance. In this view, black holes leave behind stable remnants, minuscule objects that preserve the information of everything that ever fell in. These remnants would be incredibly dense and hard to detect, perhaps even contributing to the mystery of dark matter. Others propose that evaporation continues until nothing remains, with the information somehow released in the final burst. Still others turn to speculative ideas like the fuzzball proposal from string theory, which replaces the idea of a singularity with a tangled mess of strings. No singular core, just a densely packed configuration of quantum states. In this view, the radiation process might be less like evaporation and more like the slow unraveling of a cosmic knot. Whatever the outcome, the end point of black hole evaporation challenges us to think beyond established theories. It sits at the junction of our deepest questions. What is space-time made of? Is information truly conserved? Can the universe forget? Interestingly, even classical general relativity hints at a kind of instability in the final stages. As the mass approaches zero, the curvature of space-time becomes extreme. Time and space twist so tightly that traditional equations no longer give clear answers. The final pop may be an artifact of our ignorance, a flare of energy marking the boundary where our math stops making sense. And still, the universe waits. Most black holes, especially those formed from stars or mergers, will take far longer than the current age of the cosmos to evaporate. We may never witness the final flash, but the prediction stands, patient and proud. Nothing lasts forever, not even gravity's greatest monuments. It's tempting to imagine that in some future far beyond our own, when stars have burnt out, galaxies have dimmed, and the cosmos has entered its twilight, black holes will be the last luminous things to vanish. One by one, they will release their final breath, tiny bursts of heat and light in a darkening sea, and then silence, broken only by the hum of quantum fields. Whether that silence is full of memory or empty of meaning remains one of the great unanswered questions. But one thing is certain: the death of a black hole is not an erasure, it's a culmination, a punctuation mark perhaps. The past leaves footprints in warmth, not just in cozy blankets or sun-heated stones, but in the very sky above you, an ancient afterglow known as the cosmic microwave background. This faint radiation rippling across the heavens is the universe's most enduring photograph, a snapshot taken when everything was still young and shockingly hot, and embedded within it may lie delicate clues to one of the most tantalizing cosmic possibilities: the existence of primordial black holes. Primordial black holes are not born from collapsing stars or galactic collisions. They are the hypothetical children of a much earlier age, formed in the first fraction of a second after the Big Bang, when the universe was still a frothing high-energy soup. At that time, the fabric of space-time may have experienced tiny but intense fluctuations in density. Where these fluctuations were especially large, they could have collapsed under their own gravity, forming tiny black holes. Not galactic anchors, but particles of shadow, a whisper of gravity in a universe just beginning to speak. These theoretical black holes could vary widely in mass. Some might be no heavier than a mountain, others could weigh as much as a planet. Still others, far smaller, no more massive than a paperclip, might have evaporated already, long before the first stars lit up. But if even a few have survived, they could offer explanations for several puzzles in astrophysics. Chief among them, the nature of dark matter. Dark matter is one of the grand unsolved mysteries. It neither emits nor absorbs light, but its gravitational effects are unmistakable. Galaxies rotate faster than visible matter allows. Clusters of galaxies tug on one another with extra force. Light bends more than it should, as it travels through space. Something massive and invisible is out there, and primordial black holes are one of the more exotic suspects on the lineup. To test this idea, scientists have turned to the cosmic microwave background. This radiation, first detected by Arno Penzias and Robert Wilson in the 1960s, is a remarkably uniform bath of microwave light left over from when the universe cooled enough for atoms to form. It tells us about conditions when the cosmos was just 300,000 years old, a mere toddler in cosmic terms. Instruments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured this radiation with extraordinary precision. They've mapped its tiny fluctuations, variations in temperature of just millionths of a degree, that reveal the seeds of cosmic structure. Galaxies, stars, and planets all trace their lineage back to these primordial ripples. If primordial black holes were present during this time, they would have left subtle marks. Their gravitational pull would influence how matter clumped. Their presence could distort the distribution of radiation. More dramatically, if any were evaporating via Hawking radiation during or after this era, they might have injected energy into the cosmic medium, affecting the ionization history of the universe and altering the fine structure of the microwave background. So far, the data has placed constraints. It hasn't confirmed the existence of primordial black holes, but it hasn't entirely ruled them out either. Certain mass ranges, especially in the lunar to asteroid mass range, remain viable candidates for dark matter. Other ranges are tightly constrained. If too many black holes had existed in those windows, their effects would have been noticeable. Since we don't see such signals, we know they can't dominate the cosmos. But a few, a subtle swarm, still possible, and researchers have gotten creative. In 2019, a team led by Yassine Ali Haimoud and Mark Kamionkowski proposed new methods for using gravitational lensing, the bending of light by gravity, to spot primordial black holes. If one passed in front of a distant star, it would briefly magnify the light in a precise pattern. Surveys like OGA and Subaru's Hyper-Suprime Cam have hunted for these telltale lensing events. Some intriguing signals have emerged, but the jury remains firmly in deliberation. Then came an unexpected twist. The Laser Interferometer Gravitational Wave Observatory began detecting mergers of black holes with masses in the 30 solar mass range. These are heavier than expected from typical stellar evolution, leading some theorists to suggest that at least some of them could be primordial. This idea remains debated, but it has reinvigorated interest in the field. Meanwhile, other researchers are turning to indirect signs. If small primordial black holes are still evaporating today, They could produce high-energy particles, gamma rays, antiprotons, or neutrinos. The Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer aboard the International Space Station have been scouring the sky for such signals. Nothing conclusive yet, but the sensitivity improves each year. Even the cosmic infrared background, the diffuse glow of accumulated light from distant galaxies, could hold hints. If early black holes influenced star formation or ionized hydrogen gas, they would have left fingerprints in this background, subtle shifts in its spectrum or distribution. And so cosmologists continue to dig, pixel by pixel. The search for primordial black holes is not just about solving one mystery, it touches many. If they exist, they might explain the origin of supermassive black holes in galactic centers. Perhaps these early seeds, grown by merging and accretion, evolved into the giants we now observe through radio telescopes and gravitational wave detectors. They might even help illuminate the mysterious epoch known as the Cosmic Dark Ages, the time after the cosmic microwave background formed, but before the first stars were born. Primordial black holes, if radiating during that era, would have injected energy into the gas, affecting the timing and nature of redionization. Future radio observatories like the Square Kilometre Array may be able to detect such effects. In all of this, we see a grand confluence. Tiny hypothetical black holes born in the universe's first breath could leave imprints in the most ancient light we can see, the smallest and the largest, the earliest and the latest, entwined in a cosmic dialogue. And like archaeologists brushing dust from an ancient mural, scientists keep sifting through the background, pixel by pixel, ripple by ripple, hoping to find the faint shadows of something impossibly small and impossibly old. There's something wonderfully mischievous about the idea that the universe might be a hologram. Not in the science fiction sense of a blinking simulation, but in the far more unsettling proposition that everything you experience, your teacup, your bookshelf, your swirling thoughts, could be fully described not by the space you occupy, but by a distant surface that merely encodes you. And strangely enough, this isn't some speculative afterthought. It emerges directly from the study of black holes. This idea, known as the holographic principle, finds its roots in a realization about how black holes store information. As we've discussed, the entropy of a black hole isn't proportional to its volume, as you might expect for a physical object, but to the area of its event horizon. This deeply strange result was discovered by Jacob Bekenstein and confirmed by Stephen Hawking. A black hole with more surface area, more horizon has more entropy. More stuff somehow is stored on its skin than inside its belly. That's not how normal objects behave. If you fill a box with marbles, its information content scales with its volume. But black holes defy that logic. They suggest that in certain contexts, all the information contained in a region of space can be described by what lies on its boundary, like a painting with depth projected from a flat canvas. This revelation led to a sweeping proposal by Jared Hooft and Leonard Susskind in the 1990s. Perhaps the entire universe works this way. Perhaps our three-dimensional experience is a kind of projection from a two-dimensional boundary, a cosmic hologram. The volume is real to us, yes, but its physics might be encoded elsewhere. The principle took firmer mathematical shape through the work of Juan Maldacena, whose 1997 paper introduced the CFT correspondence, a mouthful that has since become one of the most celebrated bridges in theoretical physics. In brief, Maldacena proposed a duality between two types of theories, a theory of gravity in a bulk space known as anti-de Sitter space, and a conformal field theory defined on its boundary. Everything happening in the gravitational world can be described by equations that live on the lower dimensional boundary without gravity at all. This was more than just a mathematical curiosity. It offered a testable idea. Black holes in the higher dimensional space correspond to thermal states in the boundary theory, and the process of Hawking radiation, black hole evaporation, and information retention all had precise analogues in this dual picture. The black hole is no longer a solitary mysterious creature. It becomes a reflection literally of something happening on a boundary far removed. And in this dual picture, information is never lost. The boundary theory is unitary, like all good quantum theories. If you start with a given state and evolve it forward, you can in principle reverse the process and reconstruct the past. So by this logic, black holes must preserve information too. Whatever falls in is encoded in the horizon, radiated away in subtle correlations, and eventually recoverable, at least in theory. This duality has reinvigorated hope that the black hole information paradox can be resolved. Instead of being a wall that destroys information, the horizon becomes a screen that records it. And instead of trusting gravity alone, we use its shadow on the boundary to understand its secrets. Even beyond black holes, the holographic principle has become a guiding light in the quest for quantum gravity. Some theorists, like Eric Valindi, have argued that gravity itself might be an emergent phenomenon arising from the entropic behavior of microscopic degrees of freedom. In this picture, space-time is not fundamental, it's emergent, like temperature or pressure. These are useful macroscopic properties, but beneath them lie quantum building blocks we do not yet fully understand. Such ideas sound radical, but they're grounded in the best data we have. The entropy-area relationship for black holes is not a speculative fancy, it's one of the most robust results in theoretical physics. And the correspondence between black hole dynamics and lower-dimensional quantum systems has been tested in a variety of theoretical models. While we have yet to extend the ADA's CFT framework directly to our own universe, which is not anti-de Sitter, but more de Sitter-like, the hints are compelling. Interestingly, holography offers insights not just into black holes but into cosmology. If space-time itself is emergent, then the early universe, inflation, and even the arrow of time might be understood in terms of information flow. Some models suggest that the entropy of the observable universe is constrained by the area of its cosmic horizon. Others propose that cosmic inflation can be described by holographic screens, evolving over time as information accumulates. At a more grounded level, holography has provided powerful tools for studying strongly coupled quantum systems, materials, fluids, and even quark-gluon plasmas. By mapping these complex systems to gravity-like theories in higher dimensions, physicists have made real progress in fields once thought unrelated to black holes or string theory. And yet, for all its elegance, the holographic principle remains a conjecture. We don't yet know if it applies to our own universe in full. The evidence is theoretical, the data circumstantial. Still, it changes how we think. When you look at a black hole through the lens of holography, you stop seeing it as a void. You see it as a mirror, a surface that does not consume but reflects subtly, incompletely perhaps, but without true erasure. It's humbling, really. The idea that our world, so solid, so richly layered, might be encoded on a distant screen, that what we call here is just a perspective, that the truth is waiting at the edge. And as strange as it sounds, this view may be the most complete one we have yet devised, a model in which black holes no longer defy our understanding, but teach us something fundamental about what it means to exist. Time, as it turns out, is not a universally agreed upon experience. What feels like a perfectly normal Tuesday afternoon to you might be, from a different perspective, the final breath of a star or the sluggish crawl of an eon. Nowhere is this elasticity of time more profound or more problematic than at the edge of a black hole. For black hole evaporation isn't just a game of energy and particles, it's a challenge to our very sense of when things happen, and more sneakily, whether they happen at all. Let's begin with a simple observation. General relativity tells us that gravity affects time. The stronger the gravitational field, the slower time flows, at least from the perspective of an outside observer. This isn't a poetic metaphor. It's a measurable physical truth. Atomic clocks tick more slowly at sea level than atop mountains. Satellites account for this difference daily to help your GPS stay accurate, and near a black hole, the effect becomes extreme. Time doesn't just slow, it practically halts. Imagine watching an object fall into a black hole. From your safe perch at a great distance, you'd see the object slow down as it nears the event horizon. Its motion would stretch out, its light would redshift, growing dimmer and redder until it fades entirely. In fact, it would never quite appear to cross the horizon. It would hover there, asymptotically approaching the boundary, stuck in slow motion forever. But for the unfortunate object itself, let's say a brave if unwisely adventurous astronaut, things would be very different. From their perspective, time would seem normal. They would cross the event horizon in finite time, perhaps even with a resigned shrug. Their atoms would continue forward toward the singularity. The horizon to them would not be a wall, but a coordinate crossing. This divergence in perception is more than philosophical. It's central to the puzzle of black hole evaporation. Because if a black hole evaporates over time, what does that time mean? To whom is it happening? From the outside, the black hole appears to shrink slowly, losing mass through Hawking radiation. But if objects never quite reach the horizon, if they simply freeze there, how does the black hole ever gain the mass to begin with? And if the black hole vanishes in a final burst of radiation, what happens to the frozen objects? Do they get released? Do they dissolve? Do they remain forever etched into a vanishing surface? These aren't easy questions, and they don't have consensus answers, but they illustrate the tangled relationship between evaporation and temporal perspective. Physicists have proposed several ways to reconcile this. One is the notion that the entire evaporation process should be viewed from a single coordinate frame, typically that of a distant observer. In this picture, the object never truly crosses the horizon. Instead, it becomes part of the structure of the black hole from the outside. Its information is smeared across the horizon, encoded there, and eventually radiated back out. From the viewpoint of the infalling object, however, this seems nonsensical. It crossed the horizon. It fell inward. It did not become a film on a surface. It experienced a future that the distant observer can't reconcile. The disagreement isn't just about what happened. It's about what happened even means. This conundrum deepens when you consider the implications of Hawking radiation itself. The process depends on the behavior of quantum fields near the horizon. But the location of the horizon is not a fixed point in time and space. It depends on the entire future evolution of the black hole. In technical terms, the event horizon is a global feature. It's defined by whether light can ever escape, which requires knowing the entire future of the universe. This makes it difficult to say, at any given moment, precisely where the horizon is. It's a bit like trying to draw the shore of a lake while the lake is still draining. The boundary is real, but it's not stationary, and that complicates any discussion of cause and effect near a black hole. In practice, this has led to the exploration of alternative definitions of horizons, such as apparent horizons, which are locally defined and more useful for calculations involving dynamical processes. These are the surfaces that light rays temporarily can't escape from, given current conditions. They shift and evolve as the black hole changes. But apparent horizons do not solve the information paradox. They merely offer a better tool for tracking changes. The underlying mystery remains: if the black hole evaporates, and if information is preserved, then time must accommodate both processes. The information must escape in the radiation, but without ever violating causality. The universe keeps a clean ledger, but the bookkeeping is time-delayed, perspective-dependent, and annoyingly subtle. Quantum gravity theories have tried to address this by suggesting that space-time itself becomes fuzzy at very small scales. Time may not be continuous. Events may not have a strict before and after. In some models, time is not a fundamental quantity at all. It emerges, like heat from molecules. If so, the clash between perspectives might be less a contradiction and more a misunderstanding of which clock you're using. There's a striking metaphor here in black hole complementarity, a principle advanced by Leonard Susskind and others. It proposes that no single observer can witness the violation of physical laws. From the outside, the infalling object never quite crosses. From the inside, it does. But since no observer can be in both places, the contradiction never arises. Physics remains consistent, so long as no one cheats by being two places at once. And then there's the firewall debate. If information is to escape, and if the horizon isn't just a smooth crossing but a surface of violent quantum activity, then maybe the infalling astronaut doesn't float peacefully at all. Maybe they hit a wall of radiation, a firewall that incinerates them instantly. This breaks with general relativity's promise of smooth horizons, but perhaps that's the price of saving information. Smoothness or unitarity. Pick one. Such ideas remain speculative and controversial, yet they reflect how deeply black holes challenge our understanding of time. These are not just objects of gravity, they are laboratories for causality, theaters for the drama of now versus then. One day, perhaps, when quantum gravity matures from theory into testable prediction, we'll have clearer answers. But for now, we're left in a kind of quantum intermission, where the timeline depends on where you sit. It's a strange comfort, perhaps, that in this most extreme of environments, the universe remains politely relativistic. Your experience of time is yours. The black hole, in all its stern grandeur, honors that, even if, from someone else's point of view, you never quite arrived. Among the many attempts to untangle the mysteries of black holes, string theory stands apart, less a single thread than an entire tapestry woven from the desire to unify all the forces of nature. Where quantum mechanics handles the small and general relativity rules, the large string theory aspires to bridge the gap, offering a single framework where black holes, gravity, particles, and perhaps even time itself emerge from deeper vibrating truths. At its core, string theory proposes that the fundamental constituents of reality are not point-like particles but one-dimensional strings. These strings vibrate at different frequencies, much like the strings of a violin, and each vibration mode corresponds to a different particle. A graviton, just one string's rhythm. A photon, another note on the universal scale. It's an idea both elegant and ambitious, physics reimagined as music. But what does this have to do with black holes? Quite a lot, as it turns out. One of the key tests for any theory of quantum gravity is whether it can make sense of black holes, not just their structure but their entropy, radiation and information. String theory, to its credit, made a surprising leap in this regard in the mid-1990s. In a groundbreaking paper, Andrew Strominger and Kumran Vafa demonstrated that certain types of black holes, specifically extremal black holes in a higher dimensional space, could be described in terms of strings and d-branes, which are multi-dimensional surfaces where strings can attach. By counting the number of microstates, distinct arrangements of strings and branes that correspond to a black hole with a given mass, charge and spin, they were able to derive an entropy that exactly matched the Bekenstein-Hawking area law, not approximately. Exactly. This was no small feat. It provided the first microscopic explanation of black hole entropy, using only the machinery of string theory. The black hole wasn't just a mysterious blob, it was a structured, countable object, built from strings and branes, its entropy a reflection of its hidden complexity. Since then, similar calculations have been extended to other types of black holes, though always within highly symmetric or idealized versions of the universe. The more realistic astrophysical black holes remain elusive under these techniques. Still, the results gave physicists a renewed sense of hope that the information paradox might be solved within string theory's architecture, and so emerged the fuzzball proposal, developed by Samer Mathur and others. In this picture, a black hole is not an empty shell with a singularity at its center, but rather a dense, tangled ball of strings and branes, a fuzzball. The event horizon isn't smooth or featureless, it's the outer edge of this complexity. Nothing falls into a point. Instead, it becomes entangled with the fuzz, which stores and eventually releases the information through radiation. This view has a major advantage. It avoids the formation of a true singularity, that dreaded point of infinite density where the laws of physics break down. In fuzzball theory, there is no singularity, just layers of stringy structure, resolving the paradox by replacing the horizon with something much less passive. Hawking radiation, in this model, can carry information directly, since it's emitted from the stringy surface rather than being generated at a clean, featureless horizon. But like many stringy concepts, the fuzzball remains a mathematical model, not an experimentally verified phenomenon. It works within the structure of string theory, but testing it is another story. Still, it paints a tantalizing picture that what we thought of as emptiness may be teeming with fine structure, a cosmic yarn ball waiting to be unraveled. Beyond fuzzballs, string theory also contributes to the holographic principle. As we saw earlier, Mulder-Seener's ADS-CFT correspondence provides a concrete example of how gravity and quantum field theory can be two faces of the same coin. In this context, black holes become thermal states in a boundary theory. Their evaporation and the evolution of information become processes that are easier to track. The loss of information in the bulk corresponds to a well-defined unitary process in the boundary theory. This duality, while formulated in the special setting of anti-de Sitter space, offers an interpretive lens for our own universe. Could something similar hold in the de Sitter space of our cosmology? Could black holes in our universe have a dual description where information loss becomes impossible? The mathematics is far more challenging in these cases, but the ambition remains. String theory also brings into play additional dimensions, typically 6 or 7 of them compactified into tiny shapes like Calabi or manifolds. These extra dimensions are invisible to us, but they influence the vibrational patterns of strings, and thus the properties of particles. Some theorists wonder if these dimensions play a role in black hole interiors, offering room for information to be stored, or even escape. In the grander view, string theory recasts black holes not as violations of physics, but as intricate products of it. Their entropy, their evaporation, even their paradoxes, become features of a deeper framework. Like whirlpools in a vast fluid, they hint at the properties of the medium they swirl through. That medium, in this case, is the string theoretic structure of space-time itself. Critics, of course, point out that string theory has yet to produce a single experimental prediction confirmed by observation. Its mathematical beauty is undeniable, but its physical testability remains its Achilles heel. Still, the progress made in understanding black holes has earned it cautious respect. Any theory that can explain entropy from first principles deserves a seat at the cosmic table. And so, in this stringy vision, the universe is a concert of vibrating filaments. Black holes are not silence, but dense chords, resonances of the deepest structure. Their evaporation is a slow diminuendo, their radiation a whisper from tightly bound harmonics. Whether this music will one day be heard in a detector or remain confined to the blackboard's imagination remains to be seen. But the melody, at least in theory, is consistent. And the strings, well, they're still playing. What becomes of a black hole in its final breath? Does it fizzle like an overworked light bulb, or roar like a firework launched into the silence of eternity? When the last fragment of mass evaporates through Hawking radiation, assuming it does at all, what's left behind? Ashes, sparks, secrets. The answers, as usual, are suspended in the thin air between theory and speculation. But physicists have not let the question rest. For decades, they've debated whether black holes vanish entirely or leave something behind, something dense, quiet, and deeply mysterious. Let's begin with the simplest expectation that black holes evaporate completely. In this model, they shrink steadily, their temperature climbing as their mass falls. The radiation intensifies, the process accelerates, and the final moment is a brilliant, blistering burst of high-energy particles. It's an explosion, yes, but not from internal pressure. Rather, it's the natural conclusion of a quantum process that began when a particle pair split at the horizon. The final act is an echo of all that came before, a release of energy, perhaps in the form of gamma rays, neutrinos, or other exotic particles, all pouring out in a single, unspeakably brief instant. Such a burst, if it occurred today, might be detectable by gamma-ray observatories like the Fermi telescope or ground-based Cherenkov detectors. We've not yet seen one, but that hasn't stopped researchers from looking. The idea is elegant, satisfying in its finality. A black hole that ends in a pop is a universe that keeps tidy books. Nothing left, nothing lost, no loose threads. Yet tidy books are not always the universe's style. Some physicists argue that black holes can't evaporate entirely, not because they lack the energy, but because something fundamental must remain, an object known as a remnant. This remnant, according to the theory, is a stable Planck-scale relic, unimaginably small, but incredibly dense, containing all the information the black hole ever absorbed. It's the universe's version of a compressed archive file, no longer readable by current standards, but impossible to delete. This proposal addresses the information paradox by giving information somewhere to go. Instead of being erased or scattered across the cosmos, it's locked in a microscopic prison, safe but inaccessible. The remnant acts like a cosmic USB stick, durable, cryptic, and frustratingly undetectable. But this idea raises new puzzles. For instance, if remnants exist, why don't we see them? Why hasn't one turned up in a collider, or revealed itself through gravitational lensing? And if every black hole leaves behind such a relic, what prevents the universe from being overwhelmed by these leftovers? Theoretical models must account for how remnants are produced, how many survive, and how they avoid violating the known laws of energy conservation and entropy. Then there's the issue of duplication. If Hawking radiation carries away information, and the remnant holds it too, does that violate the no-cloning theorem of quantum mechanics? This principle forbids copying quantum information. So if both the radiation and the remnant preserve the same data, something must give. Perhaps the information is split, or encoded differently, or perhaps, just perhaps, our assumptions are wrong. Enter the firewall hypothesis, another bold contender in this arena. According to this idea, the event horizon isn't a smooth, innocuous boundary, but a searing wall of high-energy particles. A firewall. Anything falling into the black hole would be incinerated upon contact, destroying the infalling observer, and along with them, any classical notion of continuity. It's a solution that preserves unitarity, the principle that information isn't lost, but at the cost of relativity's smooth fabric. Firewalls are controversial, to say the least. They challenge the principle of equivalence, a cornerstone of general relativity which holds that free-falling observers should not feel gravity. Yet, if a firewall exists, it turns the event horizon into a violent absolute end, not a crossing, but an execution. The fuzzball proposal, rooted in string theory, offers an alternative. In this view, there is no empty interior. The black hole is a tangled mass of strings and brains, and the radiation comes from its outermost layers. No singularity. No firewall, just complexity, layered, interwoven, dynamic. The information in this case never really falls in. It's absorbed into the stringy structure and gradually released, encoded in the radiation itself. And then there are more radical proposals. Some physicists entertain the idea that black holes do not end at all, but transition into something else, perhaps a new universe. This is the black hole cosmology idea, where the interior of a black hole becomes the seed of a baby universe, inaccessible from the outside. If true, then every black hole might be a cosmic womb, birthing a space-time bubble that expands, evolves, and becomes a cosmos unto itself. In such a scenario, the information paradox dissolves, not because information is recovered, but because it migrates elsewhere. The information is not lost, it's simply moved to a different narrative, one we cannot access from this side of the horizon. It's worth noting that all these ideas, remnants, firewalls, fuzzballs, cosmic maternity wards, are speculative. None has been confirmed by observation, and all depend on extensions of known physics. Yet each offers a way to preserve the laws we hold dear, especially the unitarity of quantum mechanics. There's also a possibility, however unsettling, that information is lost after all. Hawking himself initially believed this, though he later revised his stance. Perhaps our frameworks are incomplete. Perhaps the final burst of radiation is indeed featureless, a thermal discharge that dissolves memory like salt in water. If so, the universe keeps secrets not out of cruelty, but because its laws are deeper than our tools. In the end, the fate of an evaporating black hole is more than a technical issue. It's a reflection of our deepest principles: determinism, causality, conservation. To say a black hole ends in a pop or a whisper or not at all is to make a statement about what the universe allows. And as with all good endings, this one remains unwritten. There's a strange elegance in the way black holes, those notorious hoarders of matter and energy, have turned out to be some of the greatest teachers in physics. For decades they stood like shadows at the edge of our theories, quietly refusing to explain themselves. But as scientists probe deeper, mathematically, experimentally, imaginatively, the silence broke, not in words but in equations, paradoxes and quiet revelations. And what emerged is this: in trying to understand black holes, we have come closer to understanding everything else. They began as predictions, mathematical oddities from the equations of general relativity. Carl Schwarzschild discovered the first solution not long after Albert Einstein introduced his theory. At the time, few believed these solutions described anything real. They were curiosities, not celestial bodies. And yet over time the evidence mounted, from the motions of stars near Sagittarius Eristis to the ripples of space-time captured by LIGO. Black holes are no longer fiction. They are confirmed, abundant, even commonplace in the astronomical catalogue. And yet they remain deeply strange, because in black holes the known laws of physics seem to meet their match. At their center lies the singularity, where densities grow infinite and the equations break down. Wrapped around that singularity is the event horizon, a region that defines an absolute boundary in space-time, where the roles of space and time switch, where the future points inward. But thanks to Stephen Hawking's insight and the layers of theory built since, we now understand that black holes are not sealed vaults. They interact, they radiate, they shrink. In doing so, they challenge our ideas about entropy, information, causality, and even the nature of reality itself. It's in these contradictions that new understanding has flourished. The fact that black holes appear to have entropy, despite being defined by only a few parameters, mass, spin, and charge, hints at hidden structure. The emergence of Hawking radiation connects gravity with thermodynamics and quantum mechanics, a rare trinity. And the information paradox pushes us toward new frameworks, including holography and quantum gravity, with implications that ripple far beyond the physics of collapsed stars. These ideas are not confined to dusty textbooks or blackboards dense with chalk. They touch our understanding of the cosmos itself. Consider dark matter, still unknown, still invisible. Could primordial black holes, relics from the infant universe, account for some of it. Possibly, could the first stars have formed around tiny black hole seeds, altering the birth of galaxies? Quite likely, could the final flashes of evaporating black holes light up distant detectors one day? We hope so. Meanwhile, holography has changed how we think about dimensions themselves. That your three-dimensional experience might be a projection from a two-dimensional surface is not just a mathematical gimmick, it's a principle with real predictive power. It offers clues about what lies beyond space-time, and how reality might emerge from something even more fundamental. And then there's string theory, with its fuzzballs and extra dimensions, hinting that black holes might not be smooth at all, but rather tangled knots of quantum information, their horizons composed of countless vibrating filaments. These models offer ways around singularities, around paradoxes. They don't erase the mysteries, they reframe them. Black holes are also laboratories for time. Nowhere else is the relativity of time more extreme. Stand near a horizon hypothetically, and your seconds stretch into hours for a distant observer. Fall in, and you cross into a future that never returns. Watch from afar, and nothing ever seems to quite arrive. Time, space, and observation get tangled, and in the process so do we. And yet, in all this complexity, black holes are paradoxically simple. They obey a set of clean equations. They have elegant geometries. Their thermodynamics mirror that of ordinary systems. Despite being governed by gravity and quantum fields, in their extremes, they find balance. Even the final act, whether a pop, a remnant, a fizzing flash of energy, reminds us that nothing is eternal. Not stars, not empires, not even the objects we once thought immortal. Black holes, the endpoints of gravitational collapse, are not endpoints at all. They evolve, they teach, they disappear. What's left behind is not ash or mass, but understanding. We now view black holes not as cul-de-sacs in the cosmic road, but as intersections, places where physics meets philosophy, where paradox births insight, and where answers give rise to even better questions. They show us what our theories can do, and where they still falter. In chasing the light that black holes steal, we've discovered how resilient our curiosity is. We've learned to listen to the ripples of space-time, to see in darkness, to find laws in the fire of paradox. And the journey, though far from over, is already reshaping how we see the universe, and how we see ourselves in it. So thank you for wandering this long spiral of ideas with me, for floating through the quantum fog, lingering at the horizon, and tracing the last photon as it slips free from gravity's grasp. If you enjoyed this little journey into the secret life of black holes, please consider leaving a like, subscribing, or leaving a comment. Sleep well, fellow traveler.